All right, we are at noon, which means we're going to get started on our December webinar. I'm going to share just a few slides, introduce the program, and then we'll get right into the presentation. So good afternoon and welcome to the TIDC December webinar on 3D printed culvert diffuser technology. My name is Aaron Schanck, Communications Specialist for the TIDC, and I will be moderating today's webinar. The TIDC is the 2018 US DOT Region 1 University Transportation Center located at the University of Maine Advanced Structures and Composites Center. TIDC's focus is on extending the life and improving the durability of transportation assets through four research thrusts: advanced structural and performance assessment, development and implementation of novel materials, advanced structural systems and applications, and enhance performance through innovations in safety, resilience, and connectivity. TIDC has 6 member universities within the New England region: the University of Maine, University of Connecticut, the University of Vermont, the University of Massachusetts at Lowell, Western New England University, and the University of Rhode Island. Today's webinar will consist of a 30-minute presentation followed by a Q&A session. During the presentation, please use Zoom's Q&A feature for any questions you have for our presenter, and we will go down the list during the Q&A session. If we don't get through them all during the scheduled time, there will be a link at the end of the webinar to submit any further questions, and we will email you a follow-up. Our presenter today is Dr. Sunil Bhandari. Dr. Bhandari is a Transportation Infrastructure Durability Center researcher and an assistant research professor at the University of Maine. He received his BE in civil engineering from Tribhuvan University in Nepal and his MS and PhD in civil engineering from the University of Maine. Dr. Bhandari has been involved in research at the University of Maine for over 10 years and has a strong interest in structural mechanics, composite materials, especially FRP, fiber reinforced polymers, additive manufacturing, and computational modeling. Following the presentation, Dr. Bhandari will be joined by Tim Mallette of the New Hampshire Department of Transportation, a valued collaborator on this project. Tim Mallette is an engineering group leader for the New Hampshire Department of Transportation. While serving as a hydraulics engineer from 2007 to 2022, he chaired a group of champions to institutionalize 2D hydraulic modeling and a team of engineers for updating the department's drainage manual. Mr. Mallette is a member of the Interagency Silver Jackets team that helps streamline technical services and emergency responses for New Hampshire communities. Tim is active in resilient design for culverts and prioritization of projects for replacement and rehabilitation across the state of New Hampshire. So with that, the floor is yours to present, Sunil.
Okay, let me share my screen. Okay. All right. Good afternoon. I am Sunil Bhandari. I'm Assistant Research Professor at Advanced Structures and Composites Center and the Department of Civil and Environmental Engineering at the University of Maine. And I'll be joined by Tim Mallette from New Hampshire Department of Transportation during the Q&A section. So today I'm going to talk about large format 3D printed culvert diffusers for highway culvert rehabilitation. This project was done in 2 phases. The first was a prototype diffuser we 3D printed for a rural road in Thorndike, Maine. And the second diffuser we made as a part of a larger culvert rehabilitation project, which was installed in Exeter, New Hampshire. So let me go to the next slide. So we all know what culverts are. They facilitate transfer of water from one side of the highway to another, and these deteriorate with age. So this is an image of the diffuser, the culvert that we helped rehabilitate in New Hampshire. And so these culverts are designed for a certain discharge capacity, and the deterioration reduces the discharge capacity of the culverts. And with the land use change and the increased stormwater drainage in recent years and the increased rainfall has caused the discharge requirement of the culvert to be increased. So because of the deterioration of culverts and increase in discharge requirements, we have seen some culvert washouts recently in Maine. This one was at Long Dam Road, a Flagstaff in Maine. This one was at Glenburn in Maine in October 22. And this one was in South Paris, Maine in July 2023. So in order to avoid washouts and highway traffic interruptions, we need to repair or replace these deteriorated culverts. And replacing is expensive. We have to dig out the old culvert and manufacture a new culvert, place the new culvert, and repave. And it includes traffic stoppage, interruptions. So replacing is an expensive option. As an alternative to replacement, the culverts can be rehabilitated using slip lining. Slip lining is a trenchless repair technology. A smaller diameter pipe is inserted inside the existing culvert and the gap is grouted. But since the rehabilitated culvert with the slip liner has a smaller cross-section area, the discharge is reduced compared to the original design discharge. This decrease in discharge can be compensated by reducing inlet and outlet losses. The diffusers streamline the flow of water and reduce head losses. Inlet diffusers like Hydro Bell, shown here in picture, uh, are commercially available and have been successfully used to improve discharge. On the downstream side of things, outlet diffusers can be used to reduce outlet losses and improve culvert performance. The work I'm going to present today focuses on outlet diffusers. So culvert outlet diffusers are gradually flared culvert outlet sections. They can increase the culvert capacity and compensate for the losses due to liner retrofit. They also reduce outlet flow velocity and minimize erosion. And they perform best during floods when both inlets and outlets are submerged. And they are used as a part of trenchless technology for highway culvert rehabilitation. It's used as a part of a larger project, which includes slip liners, inlets, together with weirs. So the figure here shows the diffuser, which was used at, this is a diffuser that was at Mattawam Keg. This diffuser was made of fiberglass with uh, uh, fiberglass reinforcement, and this was made using wet layup. And the general dimensions are shown here of the diffuser. And similarly, this one was used. This is a plan view of the diffuser used in Exeter, New Hampshire. And the basic geometry is it's a flared pipe. If you look at the plan view, top view. So let's go to the next slide. So let's look at a CFD simulation, preliminary safety simulation to inform how diffusers can affect the flow through culverts. So The simulation, we assume the inlet head of 7.5 feet, outlet water level of 3.3 feet, and both cases have conical inlet, and one is without the diffuser at the downstream, and another is with diffuser, and the culvert diameter is 34 inches. So without the diffuser, the simulation shows that the flow discharge is 120 cubic feet per second, and with diffuser, it increases to 155 cubic feet per second. And the thing to note here is that without the diffuser, the pressure, well, with diffuser, the pressures are lowered inside the culvert pipe, and they go to a negative pressure, but the velocity is increased in the culvert. But as it reaches the diffuser section, the uh, velocity decreases, and compared to the case without diffuser, the velocity is uh, lower at the outlet. So basically, it reduces pressure head and increases velocity head to increase the flow. So why we chose to use large format additive manufacturing to make these culvert diffusers? As you can see, the geometry of each diffuser is unique and depends upon the culvert and the site conditions. The geometry is also non-prismatic with the flared section on one end and circular section on another end. And the design loads are relatively low compared to other highway structures because it is not directly under the traffic, and the backfill is lower compared to the actual culvert. The diffuser has lesser loads, and it offers significant cost reduction to other currently used methods. The only other method of manufacturing outlet diffuser that has been used is weight layup of glass fibers, and it's economically more it's economically significant cost reduction if we use 3D printing. So the figure here is the large format 3D printer in UMaine, and it can build parts up to 60 feet long, 22 feet wide, and 10 feet high. And this is the printer we used to manufacture the prototype diffuser that was used in Schanck, Maine. So we use thermoplastic extrusion-based additive manufacturing. So the idea is to take thermoplastic pellets, melt them, and extrude them from a nozzle and deposit layers of them to make a part. So this printer uses a single screw extruder mounted system, and it is mounted on a CNC gantry system. As you can see, the 3D printed part has multiple layers, and each layer has multiple beads. The parts are weaker across the layers where there are joints, and mechanical properties across the joints is comparatively lower. The manufactured part is orthotropic, and it has lower mechanical properties compared to part manufactured using other processes like injection molding. Many of us might be familiar with desktop 3D printing, which uses filaments and like they come on desktop sizes. But compared to large format additive manufacturing, the large format additive manufacturing has very high extrusion rates. The machine we saw earlier had maximum extrusion rate of 150 pounds per hour, and since that video, we have made some modifications, and now it can do up to 400 pounds per hour. And there's a newer one being made that can do up to 1,000 pounds per hour. And similarly, the build envelope of Large format 3D printers is much larger. As you saw earlier, it was for the Ingersoll machine, it was 60 feet by 20 feet by 10 feet. The feedstock material are pellets. And since large volume of polymer is being heated, there are multiple heating zones. In Ingersoll machine from the previous slide, the extruder has 4 heating zones. This helps gradual and consistent heating of polymers. Also, the beads extruded in large format 3D printing is bigger, so the surface area to volume ratio is higher. So since the beads are thicker, it takes longer to cool down, which brings us to the idea of layer time. Layer time is the time within which we need to deposit a single layer. If we take too much time, the layer will cool down too much and the layers don't stick with each other. They don't bond well together. If we deposit too fast, the layers have not become solidified enough to support the weight of another layer above it. So this limits the extrusion rate. And even though the printer can print 150 pounds per hour, we can only for 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 the parts we used in this research, we manufactured in this research, we could only print about 40-50 pounds per hour because of the limits on layer times. So the objectives of this work were to explore the feasibility of using large format 3D printer to manufacture Culvert diffusers, design, manufacture, and uh, install and monitor 3D printed diffusers in 2 phases. The first phase was diffuser prototype for experimental site demonstration. The second phase was diffuser for resilient highway culvert rehabilitation. We also wanted to assess the use of 2 different polymer system, wood flour PLA, which is a bio-based biodegradable system, and carbon fiber ABS, which is a petroleum-based system. And we wanted to see how they work for use in manufacturing culvert diffusers. We also wanted to see if we can do segmental manufacturing of the 3D printed culvert diffusers. So this is important because with segmental manufacturing, we can make parts that are larger than the build envelope of the 3D printer. And it also makes it easier to transport. And we also wanted to evaluate the material property chains of 3D printed diffusers in the field. So we wanted to see how the material mechanical properties degrade over time, and if that's acceptable for the lifespan of the structure. So comparing the two phases, the first phase was owned by Maine DOT. The diffuser was placed in a rural road in Thorndike, Maine, and we manufactured it in October 2020. The goal was so there was already a fiberglass diffuser placed. We wanted at the site. We wanted to see if a 3D printed diffuser can perform the same way. So it was for temporary trial to monitor the hydraulic performance. It was installed in 2021. We used wood flour PLA bio-based material, and the printer used was the large format Ingersoll Master Print 3D printer. And the part was 8.5 feet long and 2.5 feet wide at its widest point. And it was around 410 pounds of material, and we printed the 4 segments at once. It was divided into 4 segments, and we printed 4 of them at once. For the phase 2 of the project, the owner was New Hampshire Department of Transportation, and it was installed in Exeter, New Hampshire. We manufactured it in May 2022, and the goal was to rehabilitate corroded CMP culvert with liner and diffuser, and the diffuser was part of the larger rehabilitation project. We installed it in summer 2023. The material used was carbon fiber ABS, which is more durable and petroleum-based material, and it was suitable for structure that is supposed to that is required to last for a long time. The printer we used was another large format 3D printer we have at the Composite Center called Cincinnati BAM. BAM stands for Big Area Additive Manufacturing, and the dimension of the diffuser was 50 feet by 5.6 feet, and the total weight of the diffuser part was 1700 pounds. And for this part, we printed 4 segments independently at different times. So for the phase 1, this is the 3D model, and the circular end here connects to the outlet of the culvert, and the elliptical end, flared end discharges water downstream. The dimensions are 8.5 feet long and 2.5 feet wide at the flared end. This was experimental non-permanent installation that was installed in July 2021, and the measurement of the flow was made in October 2021 based on the hydraulic condition at site. So for phase 1 material selection, we used PLA wood pellets, which is a biodegradable material for this trial project. The diffuser was experimental and temporary, so we used bio-based material. For long-term use projects, we would go with non-biodegradable polymers. And for 3D printed part, we can do post-processing, CNC machining to get different surface finishes. But for these diffuser projects, we deemed that as printed 3D printed surface shown here was okay, was acceptable. And there are also material strength and stiffness requirements. So the manufactured part with these materials can withstand the loads. And for this project, the strength and stiffness offered by PLA wood polymer was considered sufficient. And based on the measurements done at the Thorndike site, it showed that the flow was increased by about 40% based on like the water levels, comparing just the SDP pipe and the SDP pipe with outlet, diffuser outlet and bell inlet. So for phase 1, we successfully completed phase 1. We designed, manufactured, installed the 3D printed diffuser at the site and monitored the hydraulic performance. We also saw that segmental 3D printing of long and narrow parts allowed us to have faster manufacturing times. And optimized design of culvert diffusers based on site-specific conditions. We saw that those could be manufactured using large format 3D printing at lower cost than the current methods, which is weight layup of fiberglass. So the figure here shows the experimental diffuser at Thorndike that was installed there. For phase 2 of the project, it was diffuser for culvert rehabilitation. It was part of a larger rehabilitation project of the culvert carrying Rocky Hill Brook under New Hampshire 85 Newfields Road, Exeter, New Hampshire. The culvert had deep embankment of about 20 feet, so the replacement was considered very costly. The site posed challenges in rehabilitation due to pipe capacity, and just slip lining was not good enough because it reduced the capacity. Also, there were stream crossing and wetland permitting rules that must be met to a maximum extent practicable. So a solution was a rehabilitation system which included improved inlet, liner, diffuser, and the weir. Uh, so the culvert outlet diffuser for 42-inch corrugated metal pipe liner and inlet upgrade was proposed, and it also lowered outlet velocity, which reduced erosion concern. So hydraulic design defining the internal profile and cross section was provided by New Hampshire Department of Transportation. The interior dimension and geometry was defined. The cell shape was defined. We needed to make a decision on the required thickness of the diffuser. So we characterized the mechanical properties of the 3D printed part experimentally and generated modulus in different directions. Remember, the material is orthotropic in nature. It has different properties in different directions. So we characterize the material properties and perform the finite element analysis with cell modeling and laminate analysis. And we check the stresses and deflections. We stresses on diffuser due to self weight and soil pressure is shown in the figure. We also check buckling limits. The design was controlled by buckling. So if we just printed the part with one bead wide layer, we had a buckling ratio of 1.63 for the properties of as printed materials. So if we wanted the buckling ratio to be higher because the material properties are expected to deteriorate over time, and then so we had to go with 2.8-inch wide bead layers. So we designed the joints and we manufactured the culverts using the BAAM printer here at the Composite Center. We used carbon fiber ABS material because it's more durable and can and it was deemed suitable for longer lasting structure. So it wasn't feasible to print the whole part at once because it's long. It wasn't feasible to print it in BAM. So because of the height restrictions, we printed the part in 4 different segments, one part at a time. And the segments were assembled at site. We transported them to site, and New Hampshire DOT employed a contractor to assemble it. So the printing parameters for the first segment were the polymer was extruded at a temperature of 238 degrees Celsius. The layer time for that part was 3 minutes 5 seconds, and bead width was 0.83 inch. Layer height was 0.2 inch, and because of the layer time restrictions, we could only extrude at 40 pounds per hour. Total time elapsed for printing the 4 segments was 11 hours and 42 minutes for just the first segment, and the total time for the 4 segments was 53.5 hours. And these are the 4 segments, and Professor Roberto Lopez Anido is standing there for scale, just to give an idea of how big the parts were. And this figure shows a assembled part. We assembled it in lab for a dry run. So this is assembled without any adhesive, but on site it would be assembled with adhesive for permanent installation. So this diffuser was installed in Exeter in New Hampshire in August 2023, and the part was this is a 3D model of the diffuser, and it has 4 segments connected with these design joints, and this is the outlet section. So another aspect of this study was to study the durability of the polymers exposed to the conditions at site. So we wanted to see if how long these parts will last with acceptable performance. So we conducted accelerated lab testing for durability, moisture conditioning, and freeze-thaw cycles. Accelerated water immersion test based on the principle of time temperature superpositions were performed. The idea is that uh, by increasing the temperature, we increase the rate of degradation of the polymers in lab. So assumption is that similar degradation will happen in shorter period of time. So slow degradation over long time is equivalent to fast degradation over short time. So years of degradation in field is simulated by exposing specimen in lab to similar condition but elevated temperature. So we did the accelerated testing for 3 different polymers: glass fibers reinforced PETG, wood flour reinforced amorphous PLA, and carbon fiber reinforced ABS. So the results show that the reduction in mechanical properties of carbon fiber ABS, GFPTG, and glass fiber PTG after 90 days of accelerated water immersion at 70 degrees C were within acceptable limits. There was very small loss. For WFPLA, there was significant reduction in mechanical properties, so it's not the best polymer system to use for long-term exposure. Parts with experience long-term exposure. Similarly, CF, ABS, and GFPTG worked very well and showed no significant reduction in mechanical properties after 9 cycles of freeze-thaw cycling. And again, WFPLA showed significant reduction in mechanical properties. We have also placed witness panels at site, which we plan to go back and retrieve them and test them in lab and see if they have reduced mechanical properties and by how much if they have. These are at site, and we plan to get them next year. So the conclusions for the phase 2 of the project, we successfully completed phase 2. We designed, manufactured, and installed the diffuser at site. We saw that the performance of 3D printer diffuser met the requirements. Segmental 3D printing was effective, and it allowed faster manufacturing time, easier transportation, and the produced segments are suitable for field assembly and installation. And we also found that optimized designs of Culvert diffusers based on site-specific hydraulic conditions can be manufactured using large format 3D printing of polymer composites. So this research was funded by TIDC, and funding for this project was also in part provided by STIC funds in New Hampshire. This work was performed in collaboration with Maine DOT, New Hampshire DOT, Alex Mann from Culvert Diffuser Systems, and Don LeBlanc from Delviews. So finally, we come to the questions. Thank you for listening.
Thanks, Sunil. That was great. I got the chance to go down to Exeter last summer to get some photos. And it's a really cool project. I'm excited to see where it goes in the future. We're going to open up now for Q&A. You can submit any questions using Zoom's Q&A feature at the bottom menu of your Zoom panel. You can see a little graphic there showing you where to go. And while we wait for these questions to start coming in, I have a question for both of you. Now that the Exeter installation has been in place for a little over a year, what's been your initial observations? Is it performing to expectations? Any surprises? And what are your biggest lessons learned for the project moving forward? We'll start with Sunil.
Uh, I was more involved with the manufacturing aspects, and as you know, we manufacture it using carbon fiber ABS polymer, and I think, I mean, with some optimizations, we can use recycled polymers, and we can bring down the costs of the part more significantly, and which might make it more easier to use in other projects. And with some optimizations, I think we can also increase that extrusion rate so we can manufacture it faster.
Thank you, Sunil. Any words, Tim?
Yeah, sure. And thank you for the question. I want to take just a brief minute to recognize Alex Mann and his TRB Transportation Research Board work over the years in revisiting diffusers in general. Dr. Yarnell from the 1920s had done some research, and Alex did a commendable job of literature review and then coming up with the dimensions for this circular application, which is really probably at the upper limit of 48-inch diameter. But I'd say what the takeaways have been over the past year. The constructability we knew was going to be somewhat of a challenge because we're on the tidal fringe and there were marine silts and clays down deep. So the challenge, a pleasant surprise has been the siltation on the perimeter or half perimeter of the slip lining that gives a bit of a texture. So that's maybe better than a totally smooth bore. We may have some participants from our sister agency, New Hampshire DES, and I want to recognize them too for their support of this project. It's they were very cooperative in allowing this to go forward after quite an extensive review. The outlet had to be changed to basically comply with riverine watersheds at the tidal fringe, and I would say that that's where the focus will be in moving forward. But overall, I think this was a success. The depth of water through this under a normal condition is better than what was there under the existing. I'll just leave it there because I know there's probably some more questions.
Perfect. Thank you so much. This one I think is for you, Sunil. How fancy or smart is the design of material laydown to optimize print times and structural integrity? How much of the research focuses on this part of the problem?
So again, it's a complicated problem. So again, if we lay down the material too fast, it collapses on itself. The lower layer doesn't have enough structural, it hasn't solidified enough to support the layer above it. If we lay it down too slow, it doesn't bond. So because of that, it is a complicated problem. And in this particular research, the focus was not on that. So we went with a value that works mostly.
Perfect. Thank you, Sunil. I'll field this one to you, Tim. I know you can speak to the Exeter installation. Have either of these installations seen some extreme rainfalls? How have the diffusers performed?
We haven't seen an extreme rainfall yet. We have seen some high flows, and there's been some astronomical tides as well. It doesn't really get the biennial tidal flow yet, but the projections are with sea level rise that could happen. There's a constriction in the Downeaster Railroad downstream that does control the tide as well. But this is the watershed is really pretty small. It's conservation land. However, when there's timber operations, I think there's been some increased runoff over the past few decades. We are monitoring it closely. I do think that if we get those high headwaters, it's going to transition nicely into the inlet, and the downstream condition is stable, will be stable. And we'd love to be able to do some testing here, but I think because of the changes that we made to the outlet at the end, there's going to have to be some more work before we could actually build up the headwater and discharge it and do similar testing that was done in Maine. Initially, we were thinking of putting a gate on the inlet here, a metal gate, but the cost for that came in a bit higher than I expected, and we removed that from the. So in order to test this physically in the field, we would obviously have to get some. We'd have to block off that inlet probably with a large mooring ball, maybe inflatable, that we could deflate to get up, get the depth and put the transducers in to measure the performance. But I'm pretty confident that it's based on the other data that I saw, that this is at least a 30% increase in capacity at the peak flow.
Perfect. Very interesting. Sunil, do you have any thoughts on the Thorndike installation?
Well, the Thorndike installation was a rural road, so there isn't much traffic. So, I mean, it was easier to. I mean, Alex Mann did this work, but it was easier to stop the flow and do the test. But in Exeter, it's actively used road. It's in highway, so.
Perfect. And speaking of Alex Mann, we have a question from him. Sunil, who did the CFD modeling?
Oh, this was done here at the center. The portion that was shown in this presentation, that was done here at the center.
Perfect. Thank you. Tim, how much impact to traffic was incurred with the diffuser compared to a complete replacement?
A complete replacement would have closed the road here, more than likely, because it's 2-to-1 slope on the downstream side, 3-to-1 on the upstream side. We have guardrail on one side. What they did to build the outlet was essentially a trench box with some steel sheeting above that and some sandbags on the bottom of the guardrail to control the pavement runoff. That was very nicely done by CLH and Sons, also from Maine. And they've done quite a bit of rehab for us over the years. So I mean, this isn't an extremely high traffic area, but what it is a feeder road for a larger east-west corridor in Hampshire 101, which dating back 30 years ago, we did quite a bit of work to improve the safety on that highway and remove the at-grade crossings, which this feeder road is essentially one of those crossings, one of those at-grade. So the safety was improved quite a bit. And that's where we are today. It's a ravine that was filled in a time where metal pipes were not coated. So that has affected the age of them over the years, and even though they doubled the size of the pipe that was there prior to the 1990s, it would not be approved today to do what was done in the 90s environmentally.
Perfect. Sunil, How were the segments assembled? How are they welded, sealed to make the diffuser leak-proof?
They were joined by using polyurethane adhesive at site.
All right, nice simple answer. Thank you. And for Tim, now that one diffuser has gone up in New Hampshire, given a couple more years of research, do you think New Hampshire would be open to using this technology in more culverts?
Yeah, thank you for that question. I do want to emphasize that these diffusers are they're constrained by certain slope conditions, and of course you need to backwater them at the design event, and so they're not applicable to a wide range of conditions, crossing conditions, and this particular site fit that sweet spot. And we would be hopeful that this prototype or this project essentially, along with the Maine projects, would lead us to recognize this at the alternative analysis phase, which is where it was introduced on this project. We did compare it to other alternatives, and this was thanks to the ongoing research. It was a sensible thing to do, and really want to also extend the gratitude to all of those up at TIDC and UMaine for their efforts.
Thank you very much. I think this one can go to both of you. How much of the hydraulic improvement was due to the liner versus the diffuser?
Based on the CFD simulations and the data from Thorndike diffuser, the improvement due to the diffuser, both inlet and outlet, was 30 to 40%. It was due to the diffuser.
Yeah, I would say that for this size pipe, that it would not be possible to completely match the existing condition, which was a 42-inch CMP in its original condition. Maybe with the invert completely gone, which is where we were at, the capacity would have been a little bit higher temporarily, at least. But you really need to get higher than a 48-inch diameter before that reduction in area is totally compensated by a hydrobell, for example, or any kind of improved inlet that gets your K down to 0.2 or even maybe a little lower. And then the change in the roughness of Manning's is not quite enough to get you there alone.
Awesome. Thank you very much. Sunil, the real kind of advancement in this project was the 3D printing. Do you see large-scale additive manufacturing able to be applied to other areas of transportation infrastructure?
They have been used for retrofit and rehabilitation projects, where one was so for like farm works and those kind of things. But the problem right now is the parts used for transportation infrastructure. They need to be really strong and have really good mechanical properties. And for 3D printed polymers, we have these joints which make the part weaker at these layer points joints at the interfaces. So there are some advancement where we apply continuous fiber reinforcement to the 3D printed part, and probably those parts will have more direct applications in infrastructure projects. But right now we are limited to parts that don't take a lot of load. So
All right, thank you. A question for Tim here. Tim, have you been able to evaluate the actual erosion resulting from the dispersed diffuser flow compared to that from a typical culvert overflow or outflow rather?
Yes, I think so in terms of we did have a significant event right at the it wasn't even, it was just during construction basically, and the so we were able to stabilize that a little better. What we used were granite slabs from a that were available from another box culvert, historic box culvert that was taken apart shortly before and in storage. So that in itself is a bit more stable than a normal outlet configuration. There is some sloughing ongoing, but I think because of the diurnal tidal forces further downstream, a bit outside the right of way. So it's kind of an unusual state. I'd have to say the jury's still out as far as how much of an improvement this is over what we would maybe typically do. And there may be some opportunity to improve it in the future. On that last question, I also want to just add that perhaps there could be some incorporation of sensors into the 3D into a 3D diffuser in the future that would perhaps be powered by a solar panel or something along those lines. We sort of kind of flirted with that here because of other work that was ongoing, but that would have been helpful to get pressure readings you know, at the actual peak flows.
Absolutely. That would be great. I know our partners over at UMass Lowell work a lot with sensors and fabric sensors for projects like this. So maybe
Well,
there's room for collaboration.
That's my alumni.
Gotcha. All right. Well, we're coming up on time. I'm gonna wait just a minute for any more audience questions to come in. But after that, we'll go to final words from our presenters. So I'll give just a couple seconds for any last questions to come into the chat. All right. Sunil, we'll start with you. Any final closing words for our attendees today?
So if you have any further questions, you can reach out via email. And yeah, thank you for listening.
Thanks, Sunil. Tim, any last words?
Yeah, I would just say I think this project also emphasizes the constraints that we're faced with a lot of these culverts, and we need to have an eye for rehabbing as well as the potential for connectivity between, in this case, conservation lands, but connectivity across the road that may not be able to be handled in an ideal way, but we improve the existing condition, and then we also have a means for developing future projects that could be additional improvements. And I think that's a sensible way to go about some of these rehabs. Looking forward to potential future opportunities here. And if there's any additional information or questions that people have, I'm happy to share more with them.
Perfect. Well, thank you both so much. You've been great presenters today. Please join us this coming February for our next webinar on improving the guidelines for the modeling, design, and construction of integral abutment bridges by Dr. Susan Faraji of UMass Lowell. Keep an eye out for registration for this upcoming webinar. It will be very soon. And save the date for the 2025 TIDC annual conference. It will be this August 6th through 7th at UMaine's Wells Conference Center. We're going to have a focus on composites this year, so be on the lookout for more information coming soon. If there are any questions that we weren't able to address today, I encourage you to scan the QR code or follow the link on screen. This will bring you to TIDC's Contact Us page, where there is an option to select Webinar Follow-up. This will prompt you to enter a few pieces of information so we can get back to you with your questions. And then lastly, the recording of this webinar will be available by this Friday, December 13th, and the certificate of attendance is already available to fill out in the link that's going into the Zoom chat now. So follow that link. That's right where the information page was for this webinar, and you'll be able to fill out that certificate of attendance for this webinar. And with that, thank you all very much for your time today, and have a good afternoon.
Thank you.
Thank you.